wow, we do this at higher resolution, we get better results. And let's try this in a real complicated area like Juneau. And it turned out that Carl Deerking with the Weather Service down there had been doing some initial studies on wind events there.
It's more than just having the computer resources to increase the resolution. You also have to now start including more and more physics for these small processes.
And his motivation was that in 1993, there was a very close call on an aircraft.
An aircraft departed very close to the passage of a very strong front.
Under instrument conditions, you essentially take off into the clouds straight for a mountain. And so the departure procedures say that you make a 180 degree to the right as soon as practical.
There were certain atmospheric conditions that were very brief but occurred immediately behind this front that were conducive to generating strong wind shear in the departure path of the aircraft.
And if you have some high winds, particularly changing winds coming in while you're making that sharp turn, it gets really precarious.
Strong shear caused the aircraft to roll, and once an aircraft rolls, it loses its lift and it immediately dropped.
And recovered just, I think, within 50 meters of the surface. And so that's scary stuff.
It was a near accident, but it was an accident that has been long worried about since that time, what kind of conditions could have led to this strong wind shear.
So being able to understand these wind patterns and predict them is important. So we saw this as a test case to simply see what happens if we go down the 100-meter resolution.
I wanted to try and maybe reconstruct that episode using some historical weather data of that time and see if we could learn more by doing a very high-resolution model simulation of that event.
The model we ran was just a standard weather model used all over the world these days, the Weather Research Forecasting model that we call WRF. We set it up a 9-kilometer resolution, and that was over a huge portion of Alaska. And we nested down in increments of 3. We tried to do it somewhat smoothly, from 3 to 1 kilometer, and then 330 meters down to 111 meters. And the nest at 111 meters was just over the Juneau area, the Juneau Airport area.
In the science of meteorology in particular, computer science is the whole ballgame. It's really what provides the breakthroughs. There are technological advances in instrumentation, certainly, but a lot of our ability to predict how the atmosphere will change in the future is based on computer modeling of the atmosphere. Obviously, the better observational data that's provided as input, the better the models can predict.
We put in the data where the front was far to the west of Juneau, and the front didn't actually come in until about 15 hours into our forecast. So we essentially just let the forecast run for about 15 hours, and we watched the front come through as it did in the real world. And so we certainly captured the large-scale process, the front coming in and slamming into the coast.
It's not just the wind shift itself. One of the reasons that the winds were focused so strongly in the area where the aircraft passed through was that immediately behind this cold front, the temperatures were cooling at the surface because of the front, but yet hadn't quite cooled or were still warm aloft. So we had a very temporary stable layer above the terrain where this wind shift was occurring. And as the winds are forced up the windward side of the terrain, which was opposite where the airport is, you get a downward response on the lee side of the mountains. And usually it's an accelerated wind response.
So we captured the large-scale frontal movement, but then you start looking at the smaller scale, and the process, especially right by the mountains, are really complicated. You know, if you go hiking in any mountain on a windy day, you get behind one rock, and I mean, you can be sheltered from the wind, and a few feet over, it's blasting you, and there's all sorts of eddies and turbulence going on. And so that really complicates the weather. At what they call the boundary layer, it gets really complex. And so we We modeled that and we compared it against the observations, and we've been running into a number of problems. I don't know if problems is the word, but our model output at that resolution in the areas of complex terrain are not mapping well to the observation. You get out in the flatlands, like where the airport is, you get a closer match, but in the mountains, that's where our real challenge is right now. If you want to compare your model output with an observation, and you have a specific latitude, longitude for a location, you can essentially pull out the forecast for a point in your 1 kilometer domain. And if you're off by a little ways, the terrain is so smooth anyway at 1 kilometer, it's not going to make much of a difference. But if all of a sudden you're modeling at 100-meter resolution and your grid cells aren't exactly where they should be, the latitude, longitude that we pick for an observation is about 300 meters off from its actual location. And in rugged mountains, that can be a huge difference. The data is good. We've talked with people at NCAR, we've bugged people at NCAR about this, and the data itself is good, but something goes wrong in the way that it's ingested into the weather model. There's a transformation that occurs that we're still trying to understand.
As we look to future advancements in our ability to predict weather, it will be in higher resolution in the models and in ensemble data. Ensemble data is not just running the model once, but running the model 20, 30, 40, 50 times, and looking at the variations from one run to the next, and looking for areas where the predictability is good and areas where the predictability is not so good. What you want to see is that every one of your runs is exactly the same as the other one. That would give you a high level of confidence that what you're expecting is going to work out. But if you see a high variability in a certain region, you know that the uncertainty is great in that region, and that's an area where you need to do a little more work. If your uncertainty decreases, then you have a better confidence in your forecast. So ensemble work is probably becoming more and more a common tool to meteorology these days. It starts with the old notion of a butterfly flapping its wings in China that can affect the weather in the U.S. If small-scale changes that you can't really measure over time can grow and grow and grow. These contribute error to the model. And if you can kind of capture an envelope of potential variation in these small-scale changes, then you will, in your forecast, will get an envelope of possible solutions.
At this point, we're realizing that we've got a lot of challenges ahead of us. The models themselves make certain assumptions that are valid at maybe 1 kilometer resolution, but not so valid at 100-meter resolution. And this is an area I don't really even understand very well, but it's a multi-dimensional problem. And I just sent an email out to some of the experts from Vienna last night, trying to invite them into this process here. I'm at a point where I don't understand all of the issues that well, and I need to team up with some of the people who write the code for these models.
Gets back to the butterfly flapping its wings. You have to include all of those little details.
You know, it's easy for me to just take a model and make it run on supercomputers at higher resolutions, but getting the right answers out of it, that's the atmospheric scientist part.